ketones. And we're going to see that these are going to behave almost identically, except that aldehydes are going to be more reactive in every circumstance. So makes it easy for us because any of the mechanisms that we do, if we're using an aldehyde, we can do it with a ketone. And so all of this is going to be very similar to each other. We're going to just basically call these carbonyl compounds. And let's take a look at some. Remember, an aldehyde has at least one hydrogen on it, and the ketone would have only carbons. So formaldehyde has 2 hydrogens, all the rest of the aldehydes just have 1 hydrogen, and then all the ketones have at least 2 carbons on each side. So this would be an aldehyde. This would be a ketone. And we're going to see that these are 99.9% of the time going to be electrophiles. In fact, the entire curriculum for organic chemistry for undergraduate is using these as electrophiles. There's one reaction where you can use an aldehyde as a nucleophile, but that's very, very advanced. So it's stuff that you would do in grad school if you end up continuing into chemistry. So these are very strong electrophiles. And if we just take a look at their resonance, we can see why. We see that we end up with if we just break their double bond, we're going to see that these are going to be very nice electrophiles because they have a nice positive carbon here that can be attacked by a nucleophile. So through resonance, they are good electrophiles, at least the carbons are. We also see there's some inductive effects with both of these as well. So both through resonance and induction. So in either case, these are going to be good nucleophiles, or good electrophiles. Let me try this again. Induction. There we go. We see that if we remember our carbocation stability, that this one is a bit more stable due to hyperconjugation. Because those carbon groups can donate electron density towards that positive carbon, they're going to help stabilize it. The aldehyde one has only 1 carbon group on it, so this will be less stable, and therefore more reactive. So aldehydes are much better electrophiles than ketones are. You're going to see that if we do a reaction on a molecule that has both a ketone and an aldehyde, and you only put one equivalent of your reagent, of course you're going to end up with a mess of products, but your major product will be the one that reacts the aldehyde only. And so we're going to kind of assume that when we start talking about synthesis and that sort of thing. All right. So aldehydes, ketones, both carbonyl compounds, aldehydes are more reactive than ketones are because they don't have hyperconjugation stabilizing their positive charge. All right, let's do a little bit of naming. Unless we have any questions, of course. All right, so far, we are going to introduce now 2 functional groups to our naming portfolio. And these ones are going to take priority over the ones you've learned so far. So right now, in terms of all the functional groups we've learned, we're going to see that aldehydes are the highest priority, which are higher than ketones, which are higher than alcohols, which is, I'll just put alkyl. All your alkenes, alkanes, alkynes, all those are going to be the lowest priority. So aldehydes are going to be our top priority now. then ketones, and then we're going to have alcohols. So when we're naming these, the parent chain must have the highest priority group. That's kind of the first bit. So even if it's not the longest chain, it must have the aldehyde or ketone or whatever your highest priority group is of all your groups. So right now we know aldehydes, or we're going to know aldehydes, ketones, and alcohols. So those are the things that have priority over alkyl groups. So you're always going to want to have your highest priority group as part of your main chain. And then we also want to assign the lowest possible locator number to the highest priority group. All right, and then so here are our names. So if aldehyde are the parent, we go from the alkane name and we turn it into, we end it with al. So if we have, for example, hexane, and we have an aldehyde on there, we would call it hexanal. So just like alcohols were OL, aldehydes are AL. And I'm going to give this to you now, although it is unlikely we'll see it this way. If aldehydes are a substituent, which they're not going to be right now unless we have multiple aldehydes or something, we would need something higher priority than an aldehyde, which we don't know yet. Then that becomes a formal group. So just like, you could say chloro, whatever, fluoro, whatever, this is formal, is what it would be called. Not something we're going to see right now. We could see ketones, though, as both parent and substituent. So we'll put those. If ketones are the parent, you go from your alkane name to alkanone. So you end in -one. And then if they're substituent, which could happen, they are an oxo group. For example, here's a molecule with both a ketone and an aldehyde. Aldehydes take priority, so that will be carbon 1. We would call this 3-oxohexanal. Oops. Hexanal. So here are our new bits. So aldehyde takes priority. Aldehyde will always, I can't say always. Generally, aldehydes will be carbon number 1 because aldehydes have to be terminal because they have 3 bonds already. For it to be an aldehyde, it has to have the bond to H and 2 bonds to oxygen. So aldehydes are going to be terminal. So typically we don't include a number because it's understood to be number 1 if it's your highest priority group. So, but you will need locator numbers for everything else. So we'll just do another couple of examples. Alrighty. So if you look at this, we have a couple of different functional groups here. We have got a ketone, we've got an aldehyde, and we've got a chlorine. on there, as well as, I suppose, a methyl group or something. So if we want to look at this, of all of those groups, the aldehyde is highest priority. We must give it number 1. We're going to make it as part of our main chain. So we have several ways to do this. We could say, aha, well, we have 5 carbons this way. We've got 5 carbons that way. If we look at our kind of closest point of difference, you see carbon 3 would be the chlorine. So we're going to go that direction. We're going to do the dark blue numbers. So starting at the aldehyde for number 1, we're going to go through the dark blue numbers. So even though this is not the longest possible chain you can make, it has our highest priority group. So we must start with carbon 1 as the aldehyde. All right, so let's see what we've got on this. So if we're going to use these dark blue numbers, I'm going to get rid of the light blues. Carbon 1 is our parent. We're going to leave that alone. Carbon 2, we have an isobutyl group. Or if you really want, you can say it's a, 2 methyl You can write it that way too. I would be fine with isobutyl, but do you. Carbon 3, we've got a chlorine. That chlorine happens to be in which configuration? Let's see, chlorine will be priority 1. Then, let's see, this will be priority 1, priority 2, priority 3. So this is an R for our stereochem, don't forget. So we'll just keep track of that. And then on carbon 4, we have an oxo group. And so we just need to put these in alphabetical order. So chlorine, then isobutyl, then oxo. Or if you do the 2-methylpropyl, that would be M, which still comes before oxo anyway. And then our parent name, which is pentane, becomes pentanal to indicate that we have that aldehyde. So here we go. We've got 3 chloro, 2 isobutyl, 4 oxo pentanal. And that would be how we would name this thing. All right, so we're just adding a few things to your inventory of ways to name compounds. So all of the previous rules still apply. We have same things. We have substituent names, parent names, we have stereochemistry, we have all the fun stuff. Let's do another one, and then we'll actually start talking about reactions then. So let's see. Let's do one that is shall we give this one? How about our dear friend, the sulfur? And okay, let's name this thing. So first step in naming, identify your highest priority group. Highest priority here is the ketones. We've got 2 of them, right? We've got 2 ketones here, so we want to give those the lowest possible numbers. Let's see what we can do with those. We'll start from the left, and then we'll start from the right. So in either case, our ketones will be on carbons 3 and 5. And since there's no difference from the ketones, then we now go to our next priority, which is the alcohol. So we're going to use the green numbers then, because that'll give us the lower numbers overall, and we still have our ketones as their lowest possible numbers. Of course, we technically could have started naming from or numbering from this purple one here, but that would be just silly because we clearly have a substituent on the other side anyway, so I would never do the purple one for our naming. Okay, so green numbers win here. Goodbye. Oh, let's undo that. All right, let's see. Oh, it's kind of okay. Okay, we're going to use our green numbers. So let's see what we've got on all of these. So on carbon 1, we have a hydroxy. Remember that alcohols are called hydroxy groups when they're substituents. 2, we have a methyl without any, oops. We need to have some stereochem, don't we? Let's make that a wedge. If we do that, what's our highest priority going to be for stereochem on that methyl? We look at this carbon, we see, okay, well, it's connected to 3 carbons and a hydrogen, right? Hydrogen is going to be lowest priority. It's in the dash. So we then will move one step away. What we've labeled as carbon 3 has 2 bonds to oxygen and 1 bond to carbon as we go further away. Carbon 1 has 1 bond to oxygen, and that methyl group has no bonds. So we're going to see our ketone, then this one with the alcohol, and then the methyl group. So this will be an S stereocenter. So if you remember when we talked about stereochemistry with, well, I guess we didn't, but you did, talking about stereochemistry with alkenes and alkynes, that if you have multiple bonds, they count as kind of additional connections. Remember, like a double bond counts as 2 bonds to carbon when you're comparing at the point of difference. So same thing if you have a double bond to oxygen. All right, so stereochemistry there is S. Carbon 3, we have one of our ketones. Carbon 5, we have one of our ketones, so we'll just leave those because those are going to be our parent name. Carbon 4, we have a methylthiol. Or just like methoxy would be for an ether, for sulfur, we have methylthiol is the substituent name there. Or you could say methyl mercapto, I guess, if you want to be old. But that's probably not used very much anymore. But stereochemistry here. First priority would be the sulfur. It has the highest atomic number. If we look left and right, to the right we have 2 bonds to oxygen. To the left we have 2 bonds to oxygen. Keep moving. Next carbon, carbon number 2, written there in green, has 2 carbons attached to it. Carbon number 6 on the other side has only 1. So our second priority group will be that side, and so this will be an R stereocenter. And then we have our ketones on carbons 3 and 5. And so when we have multiple ketones, we do the same thing that we did with like multiple alkenes, right? We would say like butadiene. In this case, we're going to have heptadione. So same thing. We're not going to say like 5-oxo, whatever, heptanone. We don't do it that way. Since they're both ketones, we're going to put them both as the parent name. So our parent name here is heptane. So we're going to have now hepta 3,5-dione. That would be how we're gonna go through this. So aldehydes, remember, are always carbon 1 if they're the parent. So we don't have to worry about putting numbers there because it's assumed. Hexanal has it, or pentanal has a carbon number 1 is the aldehyde. We don't have to put a 1 in anywhere for that. But because diones or ketones can never be on carbon 1, obviously because they have 2 carbons on either side, right? So they can't ever be carbon 1. We're going to need to put the numbers for the ketones. All right, so now it comes down to, once again, doing all the alphabetical order stuff. So hydroxy is first. Oops, I forgot my stereochem. 2S4R. 1-hydroxy, and then the 2-methyl will come next. I'm going to erase our parent name for now. 3-methylthiol, hepta 3,5-dione. Isn't naming things fun? I thought so. All the other rules still apply. You can have a heptadiene-dione. You can have all these crazy things. So all the same rules happen here. Okay, so that's how we're going to name these guys. Any questions on the naming part before we start talking about some of the reactions? Cool. All right, let's talk about how to make these. How to make an aldehyde. Well, in order to make an aldehyde, do we remember we have a couple ways we can oxidize primary alcohol? You can use PCC, you can use DMP, you can use a Swern oxidation. All of those will oxidize a primary alcohol into an aldehyde. So let's see. PCC is pyridine chlorochromate, if I recall. DMP, desmartin periodinane. And then Swern oxidation use oxalic chloride and triethylamine and DMSO. So all of those things can oxidize primary alcohols. You had this on your last exam. You know how to oxidize primary alcohols. So that's how we can do that. We can also do ozonolysis. Ozonolysis of a terminal. Actually, no, this is on any alkene will work. Where that gives you aldehydes or ketones, depending. And we can also do hydroboration, oxidation of a terminal alkyne. So remember, these things will all give us aldehydes if we go ahead and do those reactions. Ketones, you can oxidize a secondary oxide, oxidize a secondary alcohol using all sorts of the same reagents as above. PCC, DMP, Swern will all oxidize your secondary alcohol to a ketone. You can use the same ones. You could also use dichromate, Jones, chromic acid, AMNO4. All of those will oxidize secondary alcohols to ketones. I'm going to indicate what I meant by same. All these reagents that you use to oxidize your primary alcohol so gently to that lovely aldehyde, you could also use them on a secondary alcohol to get a ketone. So any of those, but you could also throw the more aggressive oxidizing agents on there, and you'll end up with your ketone. So the problem is you can't do that with aldehydes because they'll end up going to the carboxylic acid if you use some of these more aggressive reagents. That's why you have to use one of those first three. But the ketones, you can't really oxidize it past the ketone anyway, so you're free to use harsher reagents. Let's see, we could also do ozonolysis. Ozonolysis of an alkene. Remember that when you do ozonolysis of an alkene, you end up breaking it. So notice how on one side I get the aldehyde, one side I get a ketone, because this was an H. So you essentially remember our, oh my gosh, going nuts here, breaking that up, putting some oxygens in, and you get, in this case, both an aldehyde and a ketone out. So depending on what you have here, you can get various things. So you can use ozonolysis as well. You can do, I think, if I remember correctly, you have the acid hydration of alkynes rather, will give you a ketone or two. And then we also have Friedel-Crafts. Acylation. So remember, if we did that, if we don't take the clemensin, before you take your clemensin, you do have a ketone there. So we're going to see that synthetically. That's a great way to put a ketone on a molecule. If it's aromatic, you can go ahead and do a Friedel-Crafts acylation as well. So many ways to make ketones, more than ways to make aldehydes, but we're good. We're going to see that because these behave so similarly, now that we're going to start talking about like what to do with these things, we'll see that I'm going to just use them interchangeably because they will react the same way. And we're going to see that the reactions are all going to be fairly similar to each other. Let's take a look. Let's take a look at our first one, hydration. It's not a very exciting process, but here we go. We're going to see if we put some water, maybe just a touch of acid, we will end up hydrating our, in this case, ketone. Could be an aldehyde, doesn't really matter. However, this is kind of a very bad reaction because it really is heavily favoring the ketone form. This is called a hydrate or a geminal diol. Remember, geminal means they're on the same carbon. Two alcohols on the same carbon would be called a geminal diol or a hydrate. It's pretty boring because it doesn't really stay that way. It's not very stable. But we can still look at the mechanism. For formaldehyde, it does typically stay as the hydrate, but for every other case, it will go right back to your ketone. So what happens here? Yes, let's do that. If we're going to use the acid catalyst, first step, anytime, by the way, that you have an acid catalyzed reaction, your first step is going to be protonating something. And your last step of your reaction will be deprotonating something. So just keep that in mind. So first step here, we're going to protonate our ketone or aldehyde. And so we end up with that. Notice that now we have this protonated ketone. That's going to end up with resonance, making this a much stronger electrophile. if we just resonate this, if we move our double bond away, we can move that plus charge onto the carbon. Now this is even more electrophilic than a regular old ketone would be. So this is resonance. Either of these form, you can use either form, but what's going to happen now is we're going to have some water come in. Look who's here. It's our dear friend water. It's going to come in. We end up with now we've got now our positively charged oxygen because the water comes in. It's now got the extra proton on. And look who else is around. Oh, something to come over here and grab that extra proton, thereby giving us our product. Notice first step was protonating something, so we protonated our ketone or aldehyde. I'm just going to say ketone if that's okay with everybody. Interchangeable here. They work the same way. Protonate it, you make it much more electrophilic, gets attacked by your water. First step, protonation. Second step, nucleophilic attack. And then the last step, deprotonation. And you're done. You have your hydrated form. So again, acid catalyzed process. First thing you do, protonate something. Last thing you do, deprotonate something. So that's going to give you a hint when it comes to mechanism time that during an acid catalyzed process of any type, you should always be protonating first, deprotonating last. With base catalyzed, it's the opposite. Deprotonate first, protonate last. All right, so I'll leave this here. So pretty straightforward process. And we're going to see that this is essentially the same process for many of our reactions we're going to see here. A lot of them will be acid catalyzed. Not all of them, but a lot of them will be. And that's going to help a lot of these go forward. All right. One more thing to think about, if you're using acidic conditions, you can't use a strong base as a reagent, right? Like, it just doesn't make sense. Like, if you do that, you're just going to have an acid-base reaction and nothing's going to happen. If you remember back when you first learned the Grignard reaction, you know you can't have any alcohols in whatever you want to put your Grignard on, because alcohols are acidic. Grignards are strong bases, so you can't have, if you're wanting something to happen under basic conditions, you can't have any acids nearby. Same thing here. If we want our reaction to happen under acidic conditions, we can't have any strong bases around, because otherwise those are just going to eat up our acid, and then nothing's going to happen. So just keep those in mind too when you're designing things. Is that if you're using acidic conditions, you can't use a base. Pretty simple. So, but it's a pretty common mistake. So, you know, you can't say, I'm going to protonate this ketone, then I'm going to attack it with a Grignard. Not going to happen. Your Grignard is either going to go right after the water, it's going to go after your H3O+, it's going to go after your protonated ketone. It'll take that H off instead of attacking the carbon. So, when we're looking at these, just keep these things in mind, okay? Cool. All right, let's talk about another one. Let's do the same thing. Same reaction with an alcohol. So instead of using water, we're going to use an alcohol. Let's use methanol because that'll make our structures simple. We're going to see that if we take our ketone or aldehyde, wow, that's real ugly. Okay, let's try this one more time. There we go. Okay. If we put this with, say, some methanol under acidic conditions, we're going to see this is reversible, by the way, and that'll be a very important part. We are going to end up with methoxys now. So previously we made 2 hydroxys. One of those was from our carbonyl oxygen, and the other was from the water. With this, though, we're going to completely displace our carbonyl oxygen. And we'll see what that looks like when we look at the mechanism here. This product is called, a ketal. If you have an aldehyde that you're starting with instead, it's called an acetal. So if both your R groups are carbons, you have a ketal because it came from a ketone. If you have at least one of those R's as a hydrogen, it's called an acetal. So these are just ways of describing this. So we previously would call it a hydrate if it had the 2 hydroxys, or a geminal diol. Here we're going to call it either a ketal or acetal, depending on whether we started with a ketone or an aldehyde. So starting with a ketone, you get a ketal. Starting with an aldehyde, you get an acetal. All right, this is going to be reversible. It's all equilibrium. And that's going to be very important for us because we're going to see we can use these to protect a ketone or aldehyde if we want to do other things around it to prevent them from reacting. So, very useful reaction here. Let's take a look at it. So, first step in any acid catalyzed process, let's say we've got a protonated methanol from our acid. We're going to go ahead and protonate our ketone, or aldehyde, either one. I say minus MEOH because it's not going to come back in the next step. It is. Oh well. That we have our protonated ketone now. If we want, we can show the resonance. I'm not going to worry about it. I'm just going to say, aha, here comes our methanol. Oops, let me use the correct color. Methanol comes in. It attacks our carbon. I think I'm going to go down a little bit more because we have 7 steps for this. And in fact, here, I'll make it a little bit easier, maybe, if I do it this way. Oops. So we've moved our we now have our methanol having attacked the carbonyl. So we have this species present now. What can happen is we're going to end up doing what's called a proton shift, which is indicated by this little asterisk. Then see what happens is we have one of our groups on the same molecule just switching around where this proton is. So we end up then getting our protonated alcohol form. Hopefully so far so good. What happens next, of course? Again, same thing happens. Here comes our good friend, the methanol. Kicks out our water, because now we have a good leaving group. Again, this is all reversible. Every single step here is reversible, so we could have just kicked off our methanol again, but I mean, that's not going to be productive. It's not going to get us to where we need to go. So, but this will get us there. We lose some water. And we're going to go ahead, oops. We have our protonated form. And as I said like 5 times now, acid catalyzed process, first step, protonate something, last step, deprotonate something. So here comes either our good friend the methanol or the water. Let's use the methanol, because we're probably going to have more of that around. And we're going to end up with our product. So we lose our protonated methanol, which is what we started with. That's our catalyst, right? So we end up getting to our ketal or acetal here. Just so we know, 1, 2, 3, 4, 5. There's technically another step here that I didn't show. I did it kind of in one step where we just lose our water. If we had stopped at this stage, if we had just decided to deprotonate, if we had this thing, this one is called a Hemi Ketal or a Hemi Acetal. So again, just like with ketal acetal, if one of your R groups is a hydrogen, it's called a hemiacetal. If both are carbons, it's a hemiketal. This is kind of an unstable species. And so we're going to see here it's very difficult to isolate a hemiacetal or a hemiketal under most conditions. So either you're going to go back to your ketone or you're going to go forward to your ketal. Either way, you don't typically stop in that middle spot. So with that, this is how we can go ahead and turn our ketone into a ketal or aldehyde into an acetal. Oh my gosh, so many words. But this is the mechanism here. So protonate, attack, rearrange some protons, attack, deprotonate, done. Just be aware, this part I've done as one step. This could be you could have 3 steps for this. So some, like, I honestly, I don't remember what one weight does, if this is split up to 3 steps, or if it's in one step. I'm okay with you doing it in one. But the 3 steps would be, first you'd have your methanol or something come over, take the proton off the OMe. And then the next step, you'd have your OH then grab the proton from your newly protonated methanol. And then you'd go ahead and attack and kick out the water. It's kind of just showing that you would have some extra thing in there helping this out. I don't really need you to worry about that. So I am totally cool if you write this circled in green part just like I did right here. So using this proton shift will save you kind of 2 steps of writing them out. So save some time. You may see this fully written out sometimes. Okay, so you may see it that way. All right, notice again, everything here is reversible. You could have water come in and kick out your OMEs. So it depends what you want to do. So I'm going to go ahead and horizontalize. Oh, I guess I should mention one thing. Cyclic hemi acetals are stable. This is not something we're going to worry about right now. Don't worry about it right now, but sugars are going to typically adopt the form of hemiacetals. Oops, I put all mine the wrong way. This is glucose. Glucose predominantly exists about 98% in this form. Notice this is indeed an acetal because we have an ether and an alcohol on the same carbon. This is your hemiacetal right here. So full acetal, I'm going to just make it real obvious. This is a full acetal. 2 ethers on the same carbon. If you have the hemiacetal, you have an alcohol and an ether on the same carbon. Cyclic ones are stable, and that's something we're going to look at when we start talking about sugars. So just forget this until we talk about carbohydrates. But I just want to put that out there. So I tell you that hemiacetals, hemiketals are unstable, but in reality, cyclic ones are not. So we do see cyclic ones, hemiketals too. I'll just forget about that for now. Okay, so we will see this. I don't want anybody to be like, well, wait a second, you said hemiacetals are unstable. What's going on here? Cyclic ones are stable, but we'll worry about that later. Okay, so just don't even worry about this. I'm just putting it in your heads for later. So, again, ketone, give it some alcohol of some sort. You can do this with ethanol, whatever. H2O and H plus will get you right back to there. So you can put on the ketal or acetal and remove it pretty easily. And because this is equilibrium, we're kind of forcing this thing to take on these methanols and get rid of its water. One way we have to do this experiment-wise is you'd use a specific way to you'd need to get rid of the water that's produced during this reaction. So notice we do have water here that is produced. If you want this reaction to go all the way forward, you need to remove this. And there's many ways to do that. You can have a substance in there that will eat your water, like molecular sieves. You can use something called a Dean-Stark apparatus, which essentially does a distillation at the same time as your reaction. How that looks. Okay, this is ugly, but yuck. Okay, here is our condenser up here. As things condense, they drip down into here. This has a stopcock here. Like a burette. So we can open this as we need to. As it condenses, it fills up this portion. I'm going to use dark blue. And eventually it'll start spilling back into your reaction. Methanol is kind of a bad example here, but we're going to see that if you use something that is less soluble in water, less miscible with water, you can end up collecting all of your water here as the dark blue, and you have the rest of your solvent as the green stuff, which then pours back into your reaction, which is refluxing over here. So this is specifically designed such that when you're condensing, it drops somewhere else first, presumably separating out, and then your regular solvent goes back in. Not so much usually the case with methanol, because methanol and water are miscible, but I've done reactions like this where you're using toluene as your solvent, for example. And toluene and water don't mix. And water is denser than toluene is, so say you are using toluene as your solvent. If you're using toluene as your solvent, toluene's your green stuff. The toluene will condense up here along with any water that's present, because the water would boil too. Toluene boils at about 111 degrees Celsius. Water boils at 100. So you're boiling both. You end up condensing both, but because water and toluene are immiscible, the water stays down here. Stays out of your reaction. So the toluene fills up the rest of the kind of area in that, and will then spill back into your reaction as refluxing. So you're condensing, but just a little bit away from where you normally would. This is called a Dean-Stark apparatus. And this is just a way to help this reaction go forward. It also is great for esterification. So if you remember taking an aldehyde or alcohol and a carboxylic acid, making an ester out of those, you'll also lose water. And maybe you remember that esters can be hydrolyzed back into carboxylic acids and alcohols. This would also be a great way to prevent that from happening. So because you end up producing water as a side product, but that water could come back and reverse your reaction. So one way of preventing that. So this essentially pushes the equilibrium to the products using something like this, or molecular sieves, or something else to grab the water. So maybe some sodium sulfate or something. So remember Le Chatelier's principle, you remove a product from your reaction, you therefore push the reaction towards the products. So you thought 102 was over and the nightmares would stop? Nope. Unfortunately. So, ta-da, we've got it. Any questions on this process? This Dean-Stark thing is more for your own information. Just a way to physically help you out. So I don't think you did this in lab, but in case you were to, this would be one way to force the reaction. All right. Cool. One more thing to note is that ketals with acidic conditions, they're probably going to go reverse themselves back to ketones or aldehydes, but these are resistant to bases. And that'll be important. Because, say, if you have a ketone and an aldehyde on the same molecule, you want to get rid of the ketone but not the aldehyde. Well, a couple ways to do that. First thing, you'd probably protect your aldehyde. Remember, aldehydes are more reactive than ketones are. So if you just use two equivalents, or better yet, one equivalent of something else, if you go ahead and do this with your thing, we're going to use one alcohol. Phone's going nuts. Okay. We're going to use one alcohol. What's going to happen is we're going to fully react our aldehyde. We're going to prevent the problem of, oh, I just redrew the aldehyde. We're going to now have, this is a cyclic one, cyclic acetal, but doesn't matter. With just one equivalent of this alcohol, we can completely protect our aldehyde. And then we can now do stuff with the ketone if we want to. The aldehyde is now protected. So we can now react our ketone. If we want to get rid of the ketone, we can do a basic. So Clemenson is one way we saw to remove ketones. Clemenson is acidic conditions, so we don't want to do that. We're going to learn another one for basic conditions called the Wolff-Kishner reaction. Or we can do something else that we'll see when we talk about sulfur nucleophiles with these carbonyl compounds. But the point is, because your aldehyde is more reactive, you can protect it. If you wanted to react the aldehyde, by the way, and not the ketone, you could just do your reaction. You wouldn't need to worry about that. If you throw your Grignard in or whatever, you'll be good to go. It'll just go ahead and attack your aldehyde, because that's more electrophilic, right? But if you wanted to react the ketone, you have to block off the aldehyde from reacting. And one way to do that is to do something like this, where you're using ethylene glycol or some other dialcohol. By putting in only one equivalent of it, you're going to protect only your aldehyde. If you tried to use two equivalents of ethanol or something, you might get a mix of products. This one you'll predominantly get the acetal. Otherwise, if you don't protect it, the aldehyde is more reactive, and it will react first. And so, depending on what you want to do. Yeah, go ahead.
So with the aldehyde, the cyclic one that we just made, we could just get rid of it.
Yeah, we can get rid of it later if we want to, for sure.
Okay. So the whole point of this is just
to protect it. Yeah.
Go away.
Yep. Or do whatever you need to do. Put acid in this, you get your aldehyde right back. So yeah, for sure. So we can do Wolff-Kishner. We can do all sorts of. We can reduce this ketone back to an alcohol. We can do a Grignard reagent. We can do a nitrile. We can do. We're going to see a lot of different things that we can do now that we've protected one of them. So synthetic tool here. Use these acetals as protecting groups. They will prevent mistakes from happening, or they'll help you react the less reactive functional group. And then you can just pop it up first. So for example, if we do this, let's see. If we treat this with our dear friend the law, we will end up getting, we can reduce, as long as we don't put, I guess this needs to be a enantiomer, but you can reduce then your ketone. We'll talk about reduction later on. But this will do it. This will give you a hydride. It'll attack your ketone. This is basic because you have H minus. H minus is more of a base. We're not using any acidic conditions here. So our acetal is safe. Whoops. Guess I should indicate that's it's an acetal, right? And then we can go ahead and give it some acid, and now we are back in business with our aldehyde to do whatever. So, useful little thing here. So, if we were to just put the lithium aluminum hydride in with both the aldehyde and the ketone, we're going to react our aldehyde. And so, that's the problem with it. Okay, so if we had these two with the same conditions, we will end up getting, don't need that anymore, oops. We end up just getting an OH. So that's all it is. So it's a way of protecting your more reactive group. So first thing you'd put it on with, you use the ethylene glycol or something similar, and you would get it as a protecting group, and that'll do it. So this little bit here protects. It protects your more reactive site from reacting, and so that's how you'll use it. All right, cool. So we'll continue on Wednesday. We'll see how far we get. We'll talk about using nitrogen-based nucleophiles, using carbon-based nucleophiles, sulfur-based nucleophiles, and hydrides. Though I guess I've already shown you the hydrides. Ta-da, you reduce them. But we'll see a few more reactions next time, and we'll go from there. All right, so I have office hours today, 12:15 or so. Let's make that 12:30 if that's okay. We'll go 12:30 to 1:30. So I'll write that out for you guys. And I know that some of you have taken a look at some of your aromatic stuff and you want to ask some questions and all that. And I posted a whole ton of problems, so if you want to take a look at those, it's been brought to my attention that the key doesn't really match with the SI, so this is always a little bit, I stole those from her, less organized. So if you have done some synthesis problems and you want me to take a look, office hours is a good place to do that. So 12:30 today, 12:30 to 1:30, we'll do that here in Discord. And then Eric did ask for a review. Maybe we'll do one on Friday. I'll let you guys know on Wednesday if that's an option or not. Okay? If we do, it'll probably be the same time, like 9:10, 9 o'clock, somewhere around there. And we'll go. So, okay? But I'll let you know. Alrighty. Enjoy the rest of your day. Take care.